There's a phrase people use when they want a photonic chip to sound inevitable: matrix multiplication at the speed of light. It is a beautiful phrase. It is also the kind of phrase that makes an engineer quietly rotate a spreadsheet toward the nearest wall. The useful version is more specific. Light propagates through a waveguide extremely quickly. Waves can be split, delayed, recombined, multiplexed by wavelength, and detected in parallel with the right encoding. Those physical operations can implement weighted sums. The photonic core is not pretending to be a tiny electronic calculator. It is using physics to make the sum happen as interference and measurement. But the chip still needs to get numbers into the light. A digital memory system has to provide those numbers. A modulator has to change an optical carrier. The waveguide has loss, the phase shifters drift, a photodetector turns optical power back into a current. An ADC may turn that current into digital values. A controller calibrates the whole arrangement. The matrix operation is one part of a system, not an amulet placed over an input tensor. So the question for this episode is not whether photons are fast. Of course they are. The question is, which mathematical operation is the optical hardware actually performing? Where are the weights stored? What does the detector measure? And what happens before and after the light touches the matrix? We will build the answer from one weighted sum, then one beam splitter, then one phase shifter, then a Mach Zehnder interferometer, a mesh of interferometers, a set of wavelengths, a bank of microring resonators, and finally the electronics that keep the optical story honest. The recurring rule is simple. If a diagram says optical core, we will show the optical core. If a number comes from a company, it will wear a vendor-reported label. If a toy simulation demonstrates a mechanism, it will not be promoted into a hardware benchmark. And if the phase drift refuses to calibrate before breakfast, we will know who to call. Tung Sahur is God. The photonic chip is merely a very fast linear algebra intern with an extremely complicated commute. By the end, speed of light should sound less like a conclusion and more like the beginning of a measurement question. How much time did the laser, modulator, detector, converter, memory, and controller spend? How much energy did they use? What precision survived the trip? That is where photonic computing becomes interesting rather than mythical. There's another reason to distrust the slogan. Speed is not one number. Propagation time, modulation time, detector response, conversion time, memory time, and application latency sit at different layers. A wave can cross a millimeter-scale path in a tiny fraction of a nanosecond, while a controller spends much longer deciding what value to send. A core can produce an analog current quickly, while the system waits for a conversion or a memory transaction. The right comparison names the boundary before it names the number. The same discipline applies to energy. Photons may travel through a passive waveguide with little incremental energy, but the source still consumes power, the modulator still has a drive requirement, heaters still dissipate heat, detectors still need readout, and control loops still run. A passive optical path can be part of an efficient design without making the complete design passive. The episode will therefore keep an energy ledger visible whenever someone is tempted to turn a core property into a system conclusion. The payoff for being precise is not smaller ambition. It is a better question. If a photonic block can apply a dense matrix to many channels while using fewer expensive memory moves, that may be valuable even when the block is surrounded by electronics. If a WDM path can carry many lanes into one detector bank, that may be valuable even when calibration is non-trivial. The point is to discover where the physical representation aligns with the workload. Light is not the product. The alignment is the product. A good photonic story, therefore, has two simultaneous plots. The first plot is the physical shortcut: many channels share a propagation event. The second plot is the accounting exercise. Every interface decides whether that shortcut survives contact with the computer around it. We will keep both plots on screen instead of letting the optical path become a magical cutaway. The interesting device is the one whose advantage survives the complete journey from input memory to useful output. Start with the operation, every neural network explanation. Eventually writes on a whiteboard. Y equals Wx plus B. W is a matrix of learned weights. X is an input vector. B is a bias. E is the output that gets handed to the next layer. One entry of Y is a dot product. Take a row of W, multiply each element by the matching element of X, and add the products. Repeat that for every row. A convolution can be rearranged into a collection of these products. The projection matrices inside attention do the same kind of work. The vocabulary changes, but the hardware keeps seeing weighted sums. In a conventional accelerator, the hard part is not only the multiplication. It is moving values between memory and arithmetic units, aligning data, reading weights, writing partial sums, and repeating that dance across layers. The computation may be dense and regular, but the data movement is real. A photonic design asks whether the input values can be encoded into optical amplitudes, phases, or powers, whether the weights can be encoded in transmission or interference, and whether the detector can collect the sum efficiently. That last word matters. Efficiently does not mean magically. If a digital signal is converted into an optical signal, the conversion belongs in the accounting. If the result is immediately converted back to digital because the next operation is electronic, that conversion belongs in the accounting too. A paper may report the throughput of the optical core. A product page may report a matrix vector time. A system designer needs to know whether those numbers include laser power, modulators, ADCs, memory movement, calibration, and control. Now, separate two ideas that are often placed in the same shiny illustration. Optical interconnect uses light to move data between processors, memory pools, or chiplets that can be valuable because optical links offer bandwidth and reach. Intel's optical I/O material is an example of this category. It does not by itself establish that the link performs Y equals WX. A cable can be fast without being a calculator. Optical compute is the narrower claim. The optical path itself implements a transformation. Interference, attenuation, wavelength selective filtering, or diffraction changes the relationship between inputs and outputs. That transformation can be linear algebra, it can be parallel, it can be very fast. It can also accumulate noise and require an ADC at the exit. Our visual rule is therefore a hard line down the middle of the screen. Data movement lives on the left. The matrix mechanism lives in the center. Conversion, memory, and control live on the right. If a benchmark crosses that line, the narration will say so. If it does not, the diagram will not let the number wander across by itself. The ADC has a passport. It is not allowed to disappear at the border. A row-by-row electronic implementation often stores partial sums in registers or local memory. The weight matrix may be tiled because it does not fit in one cache or one on-chip buffer. Inputs may be reused across rows, weights may be reused across batches, and the scheduler tries to keep the arithmetic units busy. Those choices are what a photonic design is competing with. A comparison against a theoretical multiply count alone is incomplete because the electronic baseline also has a real data path. The optical version changes the representation. Instead of fetching one weight, multiplying it with one input, and adding the result in a sequence of clocked operations, the hardware prepares a field whose amplitude, phase, or power is related to the input. A physical transfer function relates the input lane to the output. Superposition performs the addition in the field or in the detector current. The parallelism is spatial, spectral, temporal, or some combination of all three. That representation creates a new question. What is the sign? A digital integer can be negative with no drama. An optical power cannot. A coherent field can have phase, so the sign may be encoded as a phase difference. A pair of positive rails can represent a difference. A reference channel can be subtracted electronically. Each choice consumes components, detector range, calibration effort, or conversion bandwidth. The simple equation y equals wx does not reveal the encoding policy, so the diagram has to. The input and output interfaces also determine whether optical compute is useful. If every small operation requires a digital to optical conversion and an optical to digital conversion, the system may spend its time translating rather than multiplying. If a whole chain of compatible linear operations stays optical, the conversion cost can be amortized, but the nonlinear and stateful parts still need a home. This is why the episode treats the optical core as a region in a graph, not as a replacement for the graph. The matrix notation also gives us a stable callback. W is the thing the hardware must encode. X is what the system must launch. Y is what the detector and electronics must recover. If one of those objects changes identity between scenes, the viewer loses the computation, even if the animation looks expensive. It also gives us a fair comparison vocabulary. An electronic accelerator and a photonic accelerator may use different mechanisms, but both must produce a useful LUI from the same X and W under a stated precision target. The question is not whether one device contains more multiplication symbols. It is whether the complete path produces the required output with lower latency, energy, or cost for the workload that actually matters. Before we build a matrix, we need to stop treating light as a glowing bead. In a photonic circuit, the useful object is a wave. A simplified complex field can be written as E of z and t equals E0 times the exponential of I times kz minus omega t. The notation compresses several physical ideas into one line. E0 is an amplitude. K describes spatial phase, advance. Omega describes temporal oscillation. The complex number keeps track of phase so that two paths can later interfere. A photodetector usually does not hand us the complex field directly. It measures a quantity related to intensity. I equals the magnitude of E squared. That means phase can be invisible at the final detector and still control the result through interference earlier in the circuit. This is the trick. A phase shifter changes a path before two paths recombine. The detector then sees a different intensity, and that intensity can represent a weighted output. The same optical carrier can also carry many wavelengths. Think of wavelength as a lane label that is physically present in the spectrum. Wavelength-division multiplexing sends several colors through the same waveguide. A filter, grating, or microring can interact more strongly with one lane than another. If each lane carries one input component, wavelength selective transmission can turn a spectrum into a bank of weighted values. The waveguide is the road, but it is not a perfect road. The optical group velocity, V sub g, tells us how the envelope of information propagates through the medium. It is not the vacuum speed of light. The material and geometry matter. Even if propagation is fast, the optical energy can attenuate. The phase can drift with temperature, and neighboring wavelengths can overlap. This is why the animation will keep four labels alive: amplitude, phase, intensity, wavelength. Amplitude and power are not interchangeable without stating the encoding. Phase is not a detector reading, it is a control over interference. Wavelength is not decoration, it is a parallel index. Intensity is not a signed number by default, which is why negative weights require balanced paths, differential detection, phase encodings, or an electronic interpretation after detection. A useful mental model is a ruler made of waves. We are not asking a photon to carry a little binary integer in its pocket. We are preparing a physical signal whose relationships can be manipulated. The computation is in the relationship. One field adds to another. One phase changes a path. One transmission attenuates a lane, and one detector sums what arrives. Once that model is stable, the word multiply becomes less mysterious. Multiplication is often an attenuation, a phase-dependent mixing coefficient, or a modulation depth. Addition is often superposition followed by detection. The hardware is not implementing the textbook symbols by writing them on silicon. It is arranging physics so that the measured output follows the same algebra over a useful operating range. The complex notation is not saying the detector is a tiny oscilloscope that reads an imaginary number. It is a compact way to preserve phase relationships while the wave travels. When two fields meet, their complex amplitudes add before intensity is measured. Equal amplitudes with the same phase reinforce. Equal amplitudes with opposite phase cancel. The detector sees the square magnitude after that addition. The interference is where phase becomes an observable change in power. In a waveguide, geometry and material determine which modes can propagate and how quickly their envelopes travel. Bends, couplers, crossings, and interfaces create loss or reflection. The chip designer has to keep the optical path stable enough that the intended phase relationship survives fabrication, variation, and temperature. The same path can be mathematically unitary in an ideal diagram and lossy in a real device. That difference is not an embarrassment. It is the reason calibration and measurement exist. Wavelength adds a second kind of identity. Two signals can occupy the same spatial waveguide while remaining distinguishable by their spectral centers. A demultiplexer or resonator can select one, but the spectrum has finite room. The source line blocked, filter shape, thermal shift, and detector bandwidth determine how close lanes can be placed before they interfere. More lanes can mean more parallel work, but also a denser control problem. The glossary will deliberately distinguish intensity from amplitude if an animation turns a bright line into a numerical weight without saying which quantity is encoded. It is visually attractive and scientifically incomplete. We will show the field, the phase relation, and the measured power as three linked views of one signal. A viewer should be able to point at the detector and say exactly what it knows and what it has forgotten. The field view is the bridge between an optical engineer's diagram and a machine learning engineer's tensor. One is continuous and complex, the other is usually quantized and indexed. The interface between them is where a compiler, modulator, calibration table, and measurement model become necessary. That interface also determines what the same number means. A tensor value may become a voltage, a modulation depth, a phase difference, an optical power, or a difference between two detector currents. The mapping is part of the algorithm. It must be inverted, calibrated, and kept within the device's usable range. Now we can build the smallest interesting photonic calculator, a Mach Zehnder interferometer, or MZI. It has a first beam splitter, two arms, a controllable phase shift in one arm, and a second beam splitter. The first splitter creates two paths. One path is delayed in phase. The paths meet again. Interference redistributes the output. Represent the first beam splitter by B using the convention B equals 1 over square root of 2 times the matrix with rows 1, I, and I, 1. The I is not a move, it records the phase relationship, introduced by this chosen ideal splitter convention. Different references choose different signs or phase factors. The physical prediction is unchanged when the convention is used consistently. Represent the phase shifter by P of phi, a diagonal matrix with 1 on the first path and e to the I phi on the second. Then the complete MZI is M of phi equals B, P of phi B. The first B mixes the input modes, P rotates one path in phase. The second B mixes them again. The output amplitudes are functions of phi, and the measured powers are squared magnitudes of those amplitudes. This is where a phase control becomes a matrix coefficient. At one phase, the two paths reinforce at the top output. At another, they cancel there and reinforce. At the bottom, a continuous phase sweep continuously changes the mixing. One MZI is therefore a programmable two-channel linear operation, with important qualifications. It is complex valued at the field level. Its detector is power sensitive, and the useful numerical range depends on calibration and noise. The code panel will use the same convention as the diagram. It will construct B, construct P for a list of phase values, multiply the matrices, and print the output for one input vector. The test will check unitarity in the ideal lossless case. It will not claim that a 2x2 simulation predicts a packaged chip. It only makes the correspondence between the equation and the path visible. The MZI also shows why optical computing is not simply multiplication at light speed. The propagation through the arms is fast. The phase control is electronic or thermo-optic and has its own response. The detector has bandwidth. The input may have passed through a DAC and a modulator. The output may pass through an ADC. The physical transform is elegant. The implementation is a system. Hold the two paths on screen long enough for the viewer to see the same two objects survive every representation. Input amplitudes become split paths. Path phase becomes a matrix diagonal. Recombination becomes the output vector. That continuity is the point. Linear algebra is not pasted over the chip. It is the bookkeeping language for what the chip is already doing. Let the input field be a two-element vector. The first B maps those two input amplitudes into two arms. P changes only the second arm. So the diagonal entries tell us which path was left alone and which path received the phase rotation. The second B maps the two arms to the two output ports. Matrix multiplication follows the path order from right to left. First, the input meets B, then P, then B again. The notation is a compact rote map. At phi equal to 0, the two arms have a particular relative phase and the output pattern is one interference state. At phi equal to pi, one arm has flipped phase and the distribution changes. Intermediate phi values produce intermediate mixtures. If the input has energy in both modes, the same block acts on both components at once. That is already a vector operation, not just a switch. The ideal matrix is lossless, so M star M is the identity under the chosen convention. A real MZI can have unequal splitter ratios, propagation loss, phase noise, thermal crosstalk, and limited phase resolution. The numerical fixture starts from the ideal case, because the ideal case makes the causal mechanism legible, the limitations chapter, then adds noise and calibration, rather than pretending the first diagram was the whole device. There is also a distinction between programming and computing. The phase control may be set slowly compared with the optical signal. Once it is set, many inputs can pass through the same transform. That is attractive for inference with reused weights. If the weights change every cycle, the control path becomes part of the workload. The MZI is fast as a signal path. It is not automatically fast as a reprogrammable memory. This is why the equation, code, and diagram appear together. The equation states the operation, the path explains the operation, the fixture verifies that the chosen symbols produce the expected numerical behavior. None of those artifacts alone is a packaged product. Together, they create an honest explanatory bridge from physics to linear algebra. The MZI is also a useful lesson in notation hygiene. The same physical device can be drawn with a different splitter convention and receive a different looking matrix. A correct explanation names the convention, tests it, and avoids treating typography as a physical law. The diagram is not decoration around the equation. It is the evidence that the equation follows the path order. That is why the code and scene share one convention. One MZI controls two modes. Neural network layers need more. The next move is not to invent a mysterious larger photon. It is to compose many two-mode operations into a mesh. Each small interferometer mixes a neighboring pair of channels. Phase shifters set the local transformation. A carefully arranged network can implement a larger unitary matrix. The word unitary matters because passive lossless interference preserves a particular notion of energy and inner product. A mesh of ideal beam splitters and phase shifters naturally gives us unitary transformations. A general real-valued neural network matrix is not necessarily unitary, so the design adds a diagonal scaling stage or uses a decomposition, such as W equals U sigma V star. U and V are unitary factors. Sigma carries singular values, which can be represented through attenuation, gain, repeated passes, electronic scaling, or another architecture-specific mechanism. This decomposition is useful and dangerous. Useful because it maps a general matrix onto physical parts with different jobs. Dangerous because a diagonal number in an equation is not automatically a free optical attenuator. Attenuation costs. Signal gain introduces noise and stability questions. Negative values require an encoding choice. A detector measures non-negative power. So, signed arithmetic may use two rails, a reference, phase-sensitive detection, or an electronic subtraction after the optical measurement. Two famous mesh layouts are the triangular Rec arrangement and the rectangular Clements arrangement. The layout is not a brand logo. It changes optical depth and loss exposure. Shorter depth can improve tolerance, but the chip still has many phase shifters and control points. As dimension grows, the number of components, calibration relationships, routing constraints, and thermal interactions grows too. Watch the visual object stay the same. Start with one MZI square, duplicate it into a row, fold rows into a mesh. The matrix becomes a grid because the physical path becomes a network. Then factor W into U, sigma, and V star. The audience should feel the scale change without feeling that the mathematics was replaced. The code trace reconstructs a small matrix with a singular value decomposition. It does not pretend to synthesize a complete photonic mesh. It demonstrates the bookkeeping. A matrix can be represented as left mixing, diagonal scaling, and right mixing. The architecture determines which of those operations are optical, electrical, lossy, calibrated, or repeated. This is the first serious limitation in the episode. Photonics gives us a beautiful way to compose linear operations. It does not make component count disappear. A matrix with a million numbers may be compactly described, but a physical implementation still needs channels, weights, memory, calibration, and a way to move signals through the device. The mesh is powerful because it is structured. It is difficult for the same reason. The mesh is a compiler target as much as it is a piece of optics. Given a desired matrix, a decomposition algorithm chooses phase settings for a sequence of two-mode operation. The settings become heater currents, carrier depletion voltages, or another device control. A calibration layer maps desired phases to physical settings. If that map changes, the compiler's answer becomes stale. Unitary factors are especially natural for coherent optics because ideal passive components preserve energy in the field. Sigma is where the desired transform asks for unequal singular values. Attenuation is physically easy to imagine, but reduces signal-to-noise ratio. Gain can compensate attenuation but can require an active device and introduce its own noise. An electronic scale after detection can preserve a digital interpretation but moves part of the operation outside the optical core. The decomposition is a map of responsibilities, not a free lunch. Mesh topology also affects calibration. A local phase error can change several downstream outputs after later interferometers recombine the path. A controller may need to measure outputs, optimize a loss function, and update multiple controls. The more channels and stages the mesh contains, the more carefully the architecture must manage observability. Reference paths, redundancy, and self-configuration can help, but they occupy area and power. The rectangular layout described by Clements is useful because optical depth and loss matter. A lower depth arrangement can reduce accumulated attenuation and make errors less severe. It does not remove the need for phase shifters, crossings, routing, detectors, and a control plane. The visual therefore grows the mesh one repeatable tile at a time and then draws a thin line from component count to calibration burden. The viewer should leave this chapter with a precise sentence. A programmable photonic mesh can represent a structured linear transform through many two-mode interference blocks. But the physical realization of a large matrix includes scaling, loss, tuning, and sign handling choices. That sentence is less flashy than the chip is doing all the math. It is much closer to what the hardware actually does. When the mesh grows, the question shifts from can it represent the matrix to can it represent, calibrate, update, and monitor the matrix under the available area and power budget. That shift from algebraic existence to physical operation is the entire engineering problem in miniature. The matrix exists on paper first, the device must keep it alive. The MZI mesh puts parallelism in spatial paths. Wavelength-division multiplexing adds another axis. Several optical carriers share a waveguide, each at a different wavelength. One fiber or waveguide can carry a small spectrum of lanes. The lanes can be modulated together, filtered separately, and detected as a collection. Microring resonators make the wavelength idea physical. A ring sits beside a bus waveguide. At wavelengths that satisfy the ring's resonance condition, energy couples more strongly into or around the ring, change the ring's effective phase or temperature, and the transmission curve shifts. In a weight bank architecture, that transmission becomes a wavelength selective coefficient. Write an input vector as x1 through xn. Put each xj on wavelength lambda j for output rho I. Arrange a set of transmission values, wij. The detector receives the weighted optical powers and produces a current proportional to their sum within the operating range. The mathematical picture is yi equals the sum over j of wi jxj. The physical picture is many colors, many transmission values, one detector node. This is not the same as saying each ring performs an exact floating point multiply. The ring has a spectral response, the modulator has finite linearity. Neighboring channels have crosstalk, the detector has bandwidth and noise. Assigned weight may require balanced encoding or a reference. The code fixture will use a toy transmission matrix to calculate a weighted sum and will label itself as a mechanism demonstration. WDM changes the scaling trade-off. Instead of placing every input on a separate waveguide, we can place many channels on one path. That saves some spatial routing, but it makes the spectrum a shared resource. Wavelength spacing, filters, thermal control, source stability, and detector bandwidth become central. A ring bank can be compact and parallel while also becoming a calibration problem with a wardrobe of nearly identical knobs. The visual compares the MZI mesh and WDM bank without declaring a winner. The MZI mesh gives coherent control over a matrix transform. The WDM bank uses spectral lanes and transmission weights. Both can compute weighted sums. Both need input encoding, output detection, calibration, and a way to represent signs and nonlinear layers. At this point, the photon has earned the word parallel. It has not earned the word free. Every lane still needs a source, a modulation strategy, a detector budget, and a calibration story. The spectrum is a beautiful shared bus. It is also a bus with traffic rules. Tongue, Sahur is God, but even God has to label the wavelengths before the detector starts summing random commuters. The microring response is a weight curve, not a magic label. A ring's resonance determines how much of a particular wavelength couples into the ring or remains on the bus. Tuning the ring shifts the response. If an input carrier sits on the shoulder of the curve, a small thermal change can change the effective coefficient. If it sits near the peak, it may be more sensitive to detuning or saturation. The operating point matters. At the detector, optical powers add naturally, that is useful for a weighted sum. But it also means the detector has a finite dynamic range. A large lane can hide a small lane, a negative contribution needs assigned representation. A calibration table can map a desired matrix coefficient to a ring control, but the table is learned from a device that has fabrication variation and neighbors. WDM can scale parallelism by reusing the same spatial waveguide. The price is that the source must maintain multiple lanes. Filters must separate them, and the spectrum becomes a shared resource. Crosstalk is not just a visual overlap. It is an off-diagonal term in the effective transfer matrix. The hardware may intend an identity selection matrix, but implement a matrix with leakage between lanes. The crosstalk fixture makes that visible by multiplying a clean lane vector by a small leakage matrix. There are also training implications. A forward path uses the device's transfer curve. A backward path needs a useful transpose or gradient estimate. If the architecture has different resources for the error path, training cost and data movement change. A WDM bank can be compelling for inference and still require a distinct training story. That is why the episode does not use neural network accelerator as a single undifferentiated label. The visual keeps the lanes colored but not rainbow magical. Each wavelength has a name, a transmission curve, a weight label, and a detector contribution. The colors are bookkeeping, the computation is the sum, the source caption identifies the microring architecture paper, while the toy code carries a mechanism-only stamp. WDM is therefore a parallel data structure with an optical implementation. The lane index is wavelength, the coefficient is transmission, and the reduction is detection. Once stated that way, the same questions used for a matrix kernel return: precision, range, signs, updates, memory, and measurement. Parallel lanes still need an address, a calibration map, and an honest detector range. A photonic core is easiest to draw when all the inconvenient boxes are missing. Let's put them back. At the beginning is a light source, a laser, an array of lasers, or a comb that provides multiple stable wavelengths. The source has power, noise, thermal requirements, and packaging requirements. The digital input lives in memory. It may be quantized, tiled, normalized, and scheduled before it reaches an electro-optic modulator. A DAC may create an analog drive signal. The modulator changes the amplitude or phase of the carrier. Then comes the photonic integrated circuit. It may contain waveguides, splitters, MZIs, microrings, gratings, phase shifters, or phase change elements. This is where the linear transform happens. It is also where propagation loss, fabrication variation, temperature sensitivity, crosstalk, and tuning complexity appear. At the output, photodetectors turn optical power into electrical current. A transimpedance amplifier conditions it. An ADC may quantize it. Digital accumulation, activation functions, normalization, and memory writes happen in electronics unless the architecture has a different mechanism. A controller monitors reference channels, updates heaters or modulators, and decides when the device needs calibration. The complete latency is therefore not just propagation. T total is T pre plus T mod plus T prop plus T det plus T ADC plus T post. The exact terms vary by design, but the accounting discipline does not. Likewise, E-total includes the laser electro-optic conversion, photonic core, optoelectronic detection, memory, and control. This is where the ADC becomes the landlord. The optical core can throw a very fast linear algebra party, but the ADC still arrives with a clipboard asking how the guests got in, how much precision they brought, and who is paying for the heating bill. The joke is not a dismissal. Conversion is a real architectural cost, and hybrid designs are often practical precisely because electronics are good at state, nonlinear logic, memory, and precision management. The hardware diagram will be drawn as a horizontal chain with two boundaries, digital to optical and optical to digital. The optical core receives a colored outline, not a halo. Every performance claim attaches to a bracket. Core only, chip level, board level, and wall-to-wall are different brackets. This also explains why an optical accelerator can be useful even when the complete machine is not purely optical. The goal may be to keep the dense, repeated linear work in a highly parallel optical path and leave control-heavy operations to electronics. Hybrid is not an admission of failure. It is a recognition that a computer is a stack of useful compromises. Packaging is where many photonic diagrams become real engineering. Lasers may be on-chip, off-chip, or co-packaged. Coupling light into the photonic integrated circuit has alignment and loss requirements. Electrical drivers sit near modulators because parasitic capacitance and bandwidth matter. Detectors need readout circuits. Thermal control needs sensors, heaters, routing, and a policy for when to retune. The memory boundary is just as important. A weight can live in a phase shifter setting, a microring resonance, a phase change material, a digital register, or an external memory. Each location changes update time, retention, precision, and energy. A fast optical multiply with a slow weight reload is useful for one workload and poor for another. A static inference service and an online learning system ask different questions of the same photonic fabric. The latency equation is not intended to predict a universal number. It is a checklist. Pre-processing may include reshaping and normalization. Modulation may include DAC output settling and driver response. Propagation may be tiny compared with the other terms. Detection may include integration time and amplification. ADC may include sampling, quantization, and interface transfer. Post-processing may include digital accumulation, activation, and memory writes. The energy equation has the same role. A passive core can have a small incremental optical energy while the laser and heaters dominate. A hybrid design can move work into electronics to reduce optical complexity while increasing conversion energy. A co-packaged system can shorten the interface while introducing thermal coupling between compute and photonic components. There is no single photonic energy term that answers every deployment question. The stack scene, therefore, shows the boxes as equal citizens. The optical core gets the visual focus because it is the novel mechanism. The surrounding boxes stay present, so the viewer cannot accidentally interpret a core-only claim as a complete machine. The ADC landlord joke is a mnemonic for the budget, not a punchline about a missing component. The system drawing is intentionally a little less glamorous than a chip close-up. It is the part that lets a viewer ask an answerable question. Which block is limiting this result? A diagram with every box is not clutter, when every box changes the claim boundary. The boxes are the measurement. AI inference is attractive to photonics for a practical reason. Many models spend a lot of time applying structured linear maps to vectors, feature maps, or token representations. A matrix can be large, regular, and repeated. A photonic circuit can expose many channels to the same propagation event. An interference or wavelength selective transmission can produce many weighted sums in parallel. Convolutions can be lowered into matrix operations, although that rearrangement may increase data movement. Attention contains projections, score calculations, and weighted combinations. Some of those operations are linear and some are not. The useful question is not, can light run a transformer? The useful question is, which subgraph is dominated by repeated linear maps, and what interface lets the optical core receive and return values without destroying the advantage? Inference is usually the friendlier first target because weights can be programmed once and reused across many inputs. Training is more demanding. Training needs forward activations, backward gradients, weight updates, optimizer state, and numerical stability. If the physical device drifts between forward and backward passes, the algorithm is no longer seeing the matrix it thinks it is seeing. If the weights live in heaters or volatile modulators, updating them may cost time and energy even when the matrix multiply is fast. The bigger conceptual issue is nonlinearity. A stack of linear transforms is still one linear transform. Neural networks gain expressive power because activation functions break that collapse. A purely passive optical mesh can perform a beautiful linear operation, but it does not automatically provide ReLU, GELU, normalization, thresholding, or softmax. The activation may happen electronically between optical layers. It may use a nonlinear material or device. It may be approximated or moved elsewhere in the graph. Every solution has a bill. Electro-optic conversion adds latency and energy. Material nonlinearities introduce fabrication and integration questions. A nonlinearity needs gain or a usable operating range if many layers are cascaded. It needs compatibility with the rest of the system. It needs calibration. A paper demonstration of one nonlinear block is important, but it is not a proof that a 100-layer model can be cascaded at the same boundary. The strongest pitch for photonics is therefore narrower and more believable. Use light where linear algebra is dense, and parallel use electronics where state, precision, nonlinear activation, memory, and control are dominant. Co-design the interface so that the two sides do not spend the entire speed up converting each other's lunch. That is not as cinematic as the whole AI model becomes a laser. It is more useful. The accelerator is a partition of work. The quality of the partition is part of the architecture. Consider a transformer block. The token matrix is projected into queries, keys, and values. Those projections are linear maps. The attention score includes a matrix product and a normalization. The weighted value combination is another structured operation. The feed-forward block contains large linear layers separated by nonlinear activations. Some portions fit an optical weighted sum engine naturally. Some portions are dominated by softmax. Normalization, memory movement, or control. Convolutional networks offer a similar split. The convolution itself has regular reuse and can be mapped to a matrix-like operation. But the image must be encoded into optical channels, and the output must be routed to the next layer. If the optical device only handles a small tile, tiling overhead and boundary handling matter. If the input is already an optical signal from a sensor, the interface may be more favorable. Workload shape is part of the accelerator design. Inference can reuse programmed weights from many samples. That makes calibration and setup costs easier to amortize. Training updates the weights and needs gradients. It also needs optimizer state, checkpointing, and numerical control. A photonic device may participate in the forward pass while an electronic system performs the backward pass. That can still be useful, but the training throughput and energy must be measured as a hybrid system. Nonlinearity is the conceptual gate. If every layer were a linear transform, the composition could be collapsed into one matrix. The network needs a function that changes the geometry of the representation. An electronic GELU or ReLU is not a small detail. It is the operation that prevents the whole optical stack from becoming a single linear map. A photonic nonlinearity may reduce conversion overhead, but it must be cascadable, stable, compatible, and energetic enough for the target depth. The correct pitch is therefore workload-specific. Photonics may accelerate a dense linear region when it can be fed continuously, when weights can stay resident, and when the result does not immediately pay a conversion penalty. It does not automatically accelerate every operation around that region. The scene draws the model as a graph with optical islands and electronic bridges, so the audience can see exactly what is being claimed. A useful compiler would expose these boundaries rather than hiding them. It could decide which layers stay optical, which tensors remain resident, when to recalibrate, how to quantize weights, and when an electronic fallback is cheaper. The photonic accelerator is then a scheduling problem as much as a device problem. The compiler is part of the optical architecture. Photonic computing is not one-chip design. It is a family of ways to make light carry a linear operation. First, coherent MZI meshes. These use amplitude and phase, beam splitters, and programmable interference to implement unitary transforms. They offer rich control over a matrix and can represent complex valued fields. Their costs include many phase shifters, calibration loss, and control complexity. The mesh is a programmable optical circuit, closer to a configurable linear algebra fabric than to a fixed filter. Second, WDM and microring arrays. These use wavelengths as parallel lanes and resonant transmission as weights. They can pack many channels onto a waveguide and perform sums at detectors. Their costs include source stability, spectral spacing, ring tuning, crosstalk, thermal sensitivity, and the challenge of representing signed values and gradients. Third, diffractive and free space systems. A spatial field passes through Machs, lenses, diffractive layers, or structured apertures. Propagation and diffraction implement useful transforms with large spatial parallelism. The architecture can be physically elegant, but input and output coupling, reconfigurability, precision, and nonlinear activation remain central questions. A passive optical image is not automatically a general-purpose neural computer. Fourth, phase change and hybrid analog system. A material state ring or programmable element stores a coefficient that persists without continuous tuning or works alongside electronics that manage the state. Non-volatile storage can reduce some programming costs. It does not remove device variability, write energy, read noise, endurance, thermal crosstalk, or the need for a system interface. The comparison is intentionally not a leaderboard. Each family answers a different question. Where are the lanes? How are weights encoded? Does the core use coherent phase or detected power? Where does the nonlinearity happen? How are weights updated? What is the benchmark boundary? The case study cards will mention research demonstrations and current product descriptions in separate colors. Light matter and light elegance claims will be labeled official product material. IBM's phase change work will be labeled a research publication page. Intel's optical I/O will sit in a separate interconnect column, so the viewer can see why bandwidth alone is not matrix multiplication. The visual payoff is a family tree made from one conserved object, a weighted lane. In the MZI branch, it interferes. In the ring branch, it resonates. In the diffractive branch, it propagates through a spatial mask. In the phase change branch, it meets a stored material state. For machines, one question: how does the hardware encode and sum a coefficient? Coherent meshes are strongest when the design wants programmable interference and complex field control. They make the matrix visible as a network of two-mode transformations. WDM banks are strongest when spectral parallelism and compact lane sharing are valuable. They make the matrix visible as a set of transmission responses. Diffractive systems use a different physical vocabulary: spatial propagation and interference across an aperture or layered mask. Phase change systems place more of the state in a material response that can persist. The same metric can mean different things in each family. Parallel might mean simultaneous spatial modes, simultaneous wavelengths, a full field passing through a mask, or many stored coefficients being read at once. Weight might mean a phase, an attenuation, a ring resonance, a pixel value, or a material state. Output might mean a power measurement, an interferometric field, an image on a sensor, or a digital tensor after conversion. This is why the family comparison uses the same 5 questions rather than a single speed bar. Where are the lanes? How are weights encoded? How are signs represented? Where is the nonlinearity? What is the measured boundary? A design that wins one answer may lose another. A compact WDM bank may have a difficult thermal spectrum. A mesh may have rich programmability, but many controls. A diffractive system may have enormous passive parallelism, but limited reconfigurability. A phase change device may store weights efficiently but require careful write and read management. The official product cards are deliberately modest. Light matter and light elegance may publish impressive capacity or efficiency figures, but the video will retain the words official product claim on the card. Intel's optical I/O example is placed beside, not inside, the compute families. This prevents a common visual error, treating every optical component in an AI system as if it performs the matrix multiply. The point of a taxonomy is not to decide which family is the future from a desk chair. It is to make future claims legible. When a new photonic device appears, ask what is encoded, what is measured, what is converted, and where the hard nonlinearity lives. The family tree is a query tool. The family comparison also protects against category drift. A photonic sensor, an optical link, a diffractive classifier, a programmable interferometer, and a phase change memory array may all contain light, but they answer different computational questions. The word photonic is a material clue, not a complete architecture. The optical core is good at a particular thing: structured linear transformation with high physical parallelism. The dream breaks when the rest of the system asks for exact, nonlinear, stable, programmable, low-energy, high-dimensional computation all at once. Start with precision. Optical values are analog. A detector current is not an infinitely precise real number. Shot noise, electronics noise, laser fluctuations, modulator nonlinearity, quantization, and accumulated error all limit useful bits. The answer is not always to demand more bit. It may be to train the model to tolerate the device's error distribution, to keep activations in a stable range, or to use differential encoding so common mode disturbances cancel. Then thermal drift. A phase shifter is a physical control and the chip lives in an environment. Temperature changes the refractive index and therefore the phase. A circuit calibrated at one time can move later. The solution is not a single calibration button. It is reference channels, monitors, feedback, lookup tables, retraining, or a control loop that spends energy keeping the matrix where the algorithm expects it. Loss and scale arrive together. More components create more opportunities for attenuation, imperfect coupling, crosstalk, and routing constraints. A mesh layout can improve loss tolerance without eliminating loss. Gain can restore signal but can add noise and stability problems. A WDM bank can add lanes without adding waveguides. But the spectrum is finite and the rings are not independent if temperature or fabrication variation couples them. Then the conversion. If a DAC drives the modulator and an ADC reads the detector, those are part of the computation's time and energy. If the next layer is electronic, moving the result back and forth may erase the optical core's advantage. If the next layer is optical, the nonlinear activation still needs a mechanism. The system can win, but only if the partition avoids conversion ping-pong. Training is harder than inference because the hardware must expose useful gradients and update weights without losing the function it just learned. Recent work explores on-chip backpropagation, but that is a research frontier, not a permission slip to claim self-training photonic clusters. Finally, benchmarks can become a magic trick. A core-only TOPS number, a per-matrix propagation time, a board-level throughput, and a wall-to-wall application latency are not interchangeable. A company's efficiency claim may be accurate at its stated boundary and still not answer a researcher's system question. The answer is a bracket on the visual. What enters, what leaves, what is included, what precision is used, what workload is measured, and who reported it. The limitations are not a funeral. They are the design brief. Every break points toward a countermeasure, and every countermeasure has a new cost. The episode will show that trade rather than hiding it behind a glowing chip silhouette. Precision is often discussed as if optical analog values simply have fewer bits than digital values. The deeper issue is that precision was workload dependent. A small absolute error may be harmless in one layer and amplified in another. A relative error near zero can be large. Saturation can clip a useful signal. Quantization can make a model robust if it is included during training and disastrous if it appears only at deployment. Noise also has structure. Detector noise, source noise, thermal drift, crosstalk, and modulator nonlinearity do not all look like independent Gaussian noise. Some are correlated across channels. Some change over time. Some depend on signal level or wavelength. A calibration routine that removes a static offset may not remove a drift or a nonlinear transfer curve. The mechanism matters because the mitigation depends on it. Loss is especially important in cascaded networks. If every stage removes a fraction of the optical signal, later stages see a lower signal-to-noise ratio. Gain may restore amplitude, but not information lost to noise. Differential paths can cancel some common disturbances while doubling hardware. Shorter meshes, better couplers, active gain, and alternative decompositions each change the area, energy, and control budget. The benchmark boundary is the final limitation because it changes the answer before the hardware does. A per-matrix core timing can be true and still fail to predict application latency. A tops per watt number can be true for a selected precision and operation mix and still not include the laser or host interface. The video will show a bracket around each reported value and refuse to let it drift into a different bracket during a transition. The limitation ledger is therefore not a list of reasons photonics cannot work. It is a list of questions any credible system must answer. How many useful bits? What noise distribution? How often recalibrate? What is the loss per stage? Where is the nonlinearity? How much energy per useful inference? Which workload? Which baseline? If the answer is not available, the visual marks the claim as unresolved rather than filling the gap with a faster animation. The honest visual language is deliberately repetitive. Mechanism, symptom, boundary, response. Repetition makes it harder for a limitation to disappear during a flashy transition. If the viewer remembers only one production habit, it should be this one. Never report acceleration without reporting what was included. If the hardware is analog, train with the hardware in mind. Hardware-aware training injects noise models, transfer curves quantization, drift, and device constraints into optimization. So the model does not learn a function that exists only in a perfect simulator. Pruning can remove work that the physical architecture cannot represent efficiently. Quantization can make the target match the available precision. None of these makes the device ideal. They make the algorithm less surprised by reality. Calibration is the second response. Use reference channels, measure the transfer function. Close the loop, keep a map from the control value to the physical response for an MZI. That may mean learning how heater settings change phase. For a ring bank, it may mean tracking resonance shifts. Calibration can happen at startup periodically, continuously, or through a hybrid strategy. Each choice trades stability against energy, latency, and complexity. Differential and balance detection can turn a signed quantity into the difference between two non-negative measurements. Common mode fluctuations may cancel. The price is extra paths and detectors. Digital analog hybrids can use photonics for the dense weighted sum and electronics for accumulation, activation, normalization, error correction, and state. The price is conversion and packaging. Non-volatile phase change elements can keep weights without constant heater power. The price is right energy, endurance, variability, and device integration. The strongest answer is often co-design. Choose the matrix layout, encoding, quantization, activation, memory placement, and software compiler together. If an optical core is fed one small tensor at a time through a slow interface, its parallelism is stranded. If the model is trained for ideal floating point and deployed onto a drifting phase mesh, its accuracy is stranded. The full stack has to agree on what a number means. Current research is also trying to make training more physical. On-chip backpropagation addresses the fact that gradients need to pass through real nonlinear and optical components. It is an important direction, but it should be reported with the same discipline as inference. What was demonstrated at what scale, under what calibration, with what conversion and control costs. Now we can define speed without a slogan. A photonic system is compelling when the workload maps to a dense linear operation. The optical parallelism is actually fed. The precision is sufficient. The conversion and memory costs do not dominate. The device stays calibrated, and the wall-to-wall result beats a meaningful electronic baseline under the same measurement boundary. That definition is less viral than matrix multiplication at the speed of light. It is also falsifiable. You can measure it. you can publish the boundary. You can find the bottleneck, you can improve the architecture. And if the calibration loop misses the beat, the margin note remains available. Zehnder is God. The benchmark still needs a power meter. Hardware-aware training can include measured transfer curves rather than idealized components. A model can learn to avoid operating points where a ring is too sensitive or an MZI is too close to a drift boundary. Quantization-aware training can match the available ADC resolution. Noise injection can make an inference model less fragile. Pruning can match the architecture's useful sparsity or channel count. These strategies move difficulty into optimization, where it can be measured and revisited. Closed-loop calibration makes the optical state observable. A reference input can test a known path. A monitor can measure a tap. The controller can compare the observation with a target and update a phase or resonance control. The loop may run continuously or only when the error crosses a threshold. The choice changes power and latency. Calibration is not free, but uncalibrated precision is not free either. It appears later as accuracy loss, retries, or a larger safety margin. Differential detection and balanced encoding address signs and common mode noise. Digital-analog hybrids place accumulation, activation, and correction where electronics have an advantage. Non-volatile devices can reduce the cost of holding weights, but right energy and endurance become part of the state management problem. Co-packaged optics can shorten links and increase bandwidth, but thermal isolation and packaging yield become system questions. On-chip training is the frontier version of the same idea. If the hardware can measure or estimate gradients through its actual nonlinear and optical elements, the training process can adapt to the device rather than assuming a perfect surrogate. A demonstration of on-chip backpropagation is valuable precisely because it attacks a difficult boundary. It is still a demonstration with a scale, workload, and measurement definition. The final benchmark should report a useful inference or training job from input memory to output memory, including the chosen precision, conversions, calibration policy, and control work. Then compare it with a serious electronic baseline under the same workload and quality target. If the photonic system wins only on the optical core, say that. If it wins wall-to-wall, show the bracket. If it does not win yet, the result is still useful because it tells engineers which term needs to shrink. That is what the last visual does. The four mitigation branches collapse into a single ledger. The equation stays visible. The photons remain fast, the benchmark becomes honest, and the Zehnder signal can finally leave the margin because the only thing it was ever allowed to worship was a properly measured system boundary. The conclusion is not pro-photon or anti-photon. It is pro-measurement. Photonics has a real mechanism for parallel weighted sums, and the surrounding system has real costs. The interesting work is finding workloads and architectures where the mechanism wins. After those costs are counted, there is a useful way to organize the final decision. First, ask whether the workload is dominated by linear maps, with enough reuse to amortize setup and calibration. Then ask whether the input can arrive in the encoding the device expects without an expensive conversion loop. Then ask whether the weights can remain resident and whether the output can stay in a compatible representation for the next operation. Finally, ask whether the quality target is robust to the device's actual error distribution. This sequence prevents a common mistake. Choosing a photonic core because it has a beautiful isolated throughput number and only later discovering that the workload spends most of its time reshaping tensors, loading weights, applying activations, or waiting for a controller. The accelerator should be selected after the graph is partitioned, not before. In some workloads, the best photonic contribution may be a single dense projection. In others, it may be an optical link that removes a memory bottleneck. In others, an electronic accelerator may simply be the better answer. The evidence ledger makes that decision reusable. A paper-reported MZI demonstration can support the claim that coherent interference implements a programmable linear transform. It cannot automatically support a claim about data center latency. A vendor-reported efficiency number can support the claim that a company advertises a product capability. It cannot automatically support a universal comparison with a GPU. An original toy fixture can support the claim that a matrix product and a transmission-weighted sum behave as shown in code. It cannot support a claim about fabrication yield or application speed. This is also why the final frame has no giant words such as revolution. It has a checklist. State the workload, state the precision, state the optical and electronic boundaries, state the calibration policy, state the memory path, state the nonlinear activation path, state the baseline, state whether the number is a paper measurement, a company claim, a local simulation, or an editorial inference. If the result survives that list, it is interesting enough without a marketing adjective. The recurring Zehnder note is allowed one last appearance because it has done its job as a memory cue. The light may propagate quickly. The phase still drifts. The detector still measures a finite signal. The controller still has to close the loop. Tung Zehnder is God. The benchmark still needs a power meter. The joke lands only after the caveat is landed. The broader lesson reaches beyond photonics. Specialized hardware is powerful when the physical representation matches the mathematical structure of the workload. It becomes confusing when a property of one layer is mistaken for a property of the whole computer. Photonic processors expose that distinction beautifully because the optical path is visibly fast, while the interfaces remain visible, if we choose to draw them. So, the final claim is intentionally conditional. Light can implement useful linear algebra with extraordinary parallelism. Photonic hardware can be good for AI when the workload, encoding, precision, memory, nonlinearity, calibration, and benchmark boundary are co-designed. It is not automatically a universal accelerator. It is a machine whose advantage appears where the equations and the physics agree. And that agreement is measurable. That is the standard the episode leaves behind.